Hi, welcome to another video on MOSFETs. So let us continue to know the region of operation of the MOSFET. So in the previous video, we have seen if I change the value of RD, or MOSFET was moving from saturation to linear region. We actually found out for a given value of VDD and VGS. So for a given specification, what was the maximum RD to keep the MOSFET at verge of saturation? In the second case, we did keep the value of RD constant. We actually varied VGS and found out what is the maximum value of VGS so that it will keep the MOSFET in saturation. Now in this, we will vary this VDD and find out for what value of VDD with RD as 1K and VGS as 0.6 volt the MOSFET remains in saturation. So now we know that this is the KVL expression for Kirchhoff voltage. Now if I write it for this loop, so this is KVL for the outer loop, which is given by VDD is equal to IDRD plus VD. Suppose if you rewrite this, VD is equal to for VDS at, so I'm looking at what is this VDD minus IDRD. So since I'm varying this, so let me, I know now what is VDS at, because VDS at is nothing but VGS minus VTH. So now I can rewrite this expression as 0.2 is equal to VDD minus, of course, for these specifications, ID comes out to be 0.2 milliampere. It is 0.2 milli into 1K. So this will become, now I can actually find out what is. So this is what is the minimum VDS you should have, sorry, VDD you should have to keep the MOSFET in saturation. So what is VDD minimum? So it is 0.2. I'm just feeding the equation as it is. 0.2 alpha equals, so this is a variable, I'll put it as alpha A minus 0.2 milli into 1K will become just 0.2. It is 0. Okay, let me just put it as 0.2 exponential minus 3 into 1 exponential 3, of course, which you can write it as simply 0.2. So now I have to do shift cal. So now VDD minimum happens to be 0.4, meaning I should keep the voltage of this at 0.4 volts, then only the MOSFET will be in saturation. Otherwise, if you keep the voltage less than 0.2, it will be in linear region. Any voltage beyond 0.4, the MOSFET will be in saturation. That's why I'm writing VD minimum. So now, okay, in the previous case, whatever VGS, I got it as this. This is the maximum voltage of VGS that you can keep to keep the MOSFET in saturation. Here also this was RD max. So RD max was 8K. Here VGS max is 0.908 volts. Here VDD minimum is 0.4. If I keep any voltage beyond 0.8, it is fine to keep the MOSFET in saturation. If the value of VDD is less than 0.4, for these specifications, MOSFET will be in linear region. So let me go back and try to verify, are we getting the same thing or not. I'm actually ranging from changing this VDD from 0 to 2.5 volts with an increment of 0.01. So let me run this. Now if you see this, because I know that, okay, what is the value of suppose if I see, so what is this? This is VGS 0.6. So I should look at where it will become minimum 0.2. So 0.2, if you see this, just have a look at this. So this should be 0.2. This is what, okay, I'm looking at 0.2. Where is 0.2? Just have a look at this vertical. So this should be 0. That is 200 millivolt. For that 200 millivolt, what is the corresponding VDD? That is, if you see here, I'm there at almost there at 200 millivolt. Let me just zoom it and see. Let me make it close to 200. Now it's exactly 200. See here, this is the vertical, which is nothing but VD, that is this voltage, that is drain to source voltage. Since VGS is 0.6, I should get VD as 0.2 to keep the MOSFET in saturation. So for VD to be 0.2, the VDD needs to be 400 millivolt. That's what is here. Let us go back and see here. If this is 0.4 with this as 0.6, it results in a current of 200 microampere, which will result in a 0.2 volt drop here. Out of this 0.4, if 0.2 drops here, so minimum, of course, the remaining will be 0.2, which will keep the MOSFET in saturation. If you keep the voltage more than 0.4, then more and more drop will happen. So suppose if you make it 0.5, then this will be 0.2 will be dropping here, then this will be 0.3 will be remaining. If you make it 0.8, 0.2 is dropped here, and this will be 0.6. So for all voltages above 0.4, MOSFET is in saturation. If you go a voltage less than this, then the current will reduce. So that you can see here also. What you can do is, for any voltages beyond 400 millivolt, you can see VD is more than 200. So VD is more than 200. And if you actually see a plot of current also, maybe up to, okay, let me just zoom it out, up to VD, sorry, up to VDD of 0.2, current will be, okay, after this current will be constant at 200 microampere. So let me add that trace, add trace. What is that I'm supposed to trace? This is this. See here, is the current constant here? Maybe we'll just change the color. Change the color to maybe this. See here, the current is constant at 200. Suppose if I just go here, can you see the current is 200? Now it is saturated. So from here onwards, current is saturated, which is exactly 400 millivolt. Suppose if I zoom it and then just try to bring it back here, you can see I'm there almost. So at 400 millivolt of VDD, current becomes saturation, that is current becomes 200 microampere, which is the saturated current. Okay, that way we can able to verify each and every calculation that we do in the paper design can be verified in simulation. Okay, now we'll just move on to using this MOSFET for amplifier. So we know that, okay, we have a signal here. We have a signal here. That signal need to be amplified. So this signal will have, okay, two terminals, plus and minus. So there is a reference, and this one I'm going to have the amplifier. I'm going to have the amplifier here, and there will be a, okay, assume that this is a audio amplifier. So this is the signal coming from a mic. There is an audio amplifier, and you have a speaker, So this will be connected to this, and there are two terminals again for the op-amp inputs. Sorry, amplifier input. This is plus and minus. Minus is usually grounded, and this output speaker. So suppose if it is a speaker, then this will also have two terminals. One is plus, other is the ground, which is this. So usually these two will be same. You can as well treat it as so and so. So this is plus of it. So this is what? This is the input. This is output. So in this first analysis, let us take a small signal. So let us take a small AC signal. And of course need to be amplified so that it can be driven, or it can be given to the speaker. So now we want to develop an amplifier which will amplify this small AC signal to a larger amplitude so that it can drive the load. Now when I say small AC signal, its amplitude is relatively small, maybe in terms of few millivolts, hundreds of millivolts. Now when I say AC signal, so AC signal is one whose value is symmetric about the zero line. So this is, if it is with respect to time, if this is the area on the positive half, if this is the area on the negative half, for a pure AC signal, area on the positive half is equal to area on the negative half. When I say negative half, it is below 0, this is above 0. Now this is a type of signal that you have. Since it is small in magnitude, I will say it as small AC signal. Now assume that if I want to amplify this signal using a MOSFET amplifier, so let me just take it as a MOSFET. So this is my MOSFET, and if I apply this small AC signal to this as it is, so this is grounded, and let me just connect it here. So before we connect something here, let us see what happens. So let us assume that this is of amplitude 100 millivolt and this is minus 100 millivolt. Assume that this is a sinusoidal signal at certain frequency, maybe 10 kilohertz, 20 kilohertz, or 5 kilohertz, whatever. So now you are applying a signal which is AC, which is above 0 and below 0. Now assume that you have connected some resistor here. This is connected to 1.8 volt. Now since the amplitude is okay, we also know that the transfer characteristics of this is given by something like this. So this is what we saw in one of the video previously. This is what VGS, this is ID. So what is the type of signal that you are applying between gate and source? You are applying a small signal, and of course we know that this is 0 current as well as 0 voltage. So this is 0 and this may be around 0.4 volt. Beyond 0.4 only this will conduct. So you're going to have some currents, okay, depending on what is the W equivalent, all those stuff. Now what I actually have is I am applying a signal which is varying around 0. So now shall I say this is my signal. So during positive half cycle this goes above 0, and during negative half cycle does this go below 0? Can you see this is the type of signal that you are applying to this MOSFET? If this is the type of signal that you are applying, can you see is this entire region of your input signal is in this region? So shall I say now this as cutoff region? Here the MOSFET is off actually. Here the MOSFET is on. Here it is on. In on there can be two possibilities. Either it can be in linear region or it can be in saturation region. For both of them the condition is VGS should be greater than VTH. For this VDS can be less than or equal to VDS sat. For this condition is must. Along with that VDS has to be greater than VDS sat. So these are some specifications what we learned in the previous videos. Now assume that you have a situation where you're having a small AC signal of amplitude 100 millivolt. 100 millivolt here at the top, and here at the bottom it is minus 100 millivolt. This is 0. This is with respect to time you're applying. So this entire AC signal, since it is around this point and it is always in the cutoff region, you cannot amplify this signal as it is now. Why? Means the MOSFET is totally off during the entire transition of your input signal. So what you're actually looking for is you are having a small AC signal which need to be amplified, and its amplitude should be increased. Shape should not be lost. But what's happening here is the entire signal is not sufficient to turn on the MOSFET. So what I have to do now, I have to make sure that this should somehow come here. So I'll just move this from here to here, and I'll just come somewhere here. If I come somewhere here and apply, now can you see here, you're actually applying the AC signal here. Now you actually move the AC signal from here to here. Why you are supposed to move? Because here the MOSFET was completely off. Now you do something, you first make the MOSFET to turn on. So that's what is this. Let me just put it in a different color. So this green one is ensuring that MOSFET is on, and over and above that I'm applying a small AC signal. So now the one which is used to make the MOSFET on permanently is 1 voltage. Let me say it as capital VGS. The one which is varying, let me call it as small VGS. This is a DC signal, this is a AC signal. So how do I achieve this over here? So I said no, there is no capital VGS at all. So whatever you have is a small signal. So on top of this you add one more VGS, meaning I'll be adding one more VGS. So what is this? This is VGS. This is V in, which I'll call it as small VGS. That is a small input signal. This is the DC signal. This is the DC signal. So now let us see what is the impact of this on this. So okay, let us maybe we will not exactly see the amplification. Let us see whether the MOSFET will be on or not. So how do we achieve this? Let me just go back to my circuit. So now what I'll do, I will do some changes. This is my okay. In order to get the sine wave, I can go over here. Can you see this is sine? This is sine. You can give the offset. So now whatever 0.6 what I wanted, I can actually, or let me just give it as 100 milli, and this is 10 kilohertz. So I'm applying a 100 millivolt signal, 10 kilohertz. This is done. So I'm applying a sine wave of 100 millivolts also. Let me also put a DC source. So what I'll do is, let me slightly modify the circuit. So what I'll do is, I'll just take this, drag it bit down so that I can be comfortably drawing the plot. Next I will take one more power supply. I'll go here. Either I can take this, or there is, if you want to see a battery like power supply also, there is something like miscellaneous. So click on this, you can see, double click for miscellaneous. If I click, can you see there is a battery? So this is a battery. I can just put it here. Now I can use this for 0.6. This is that 0.6. This is a sine wave. So let us assume that okay, we have W bell as, maybe let me increase the W bell to maybe around 1000, so that W bell becomes 100 now. So 1000 by 100, so 1000 by 10 will be 100. So W bell will be 100. And for all these things, so I think I'll get a drain current of 400 microampere. 400 microampere. So let me just check out what happens. Now if you actually see the input waveform here, suppose if I now, what is the type of signal that you want to see now? Suppose if you see here, do you want to see a sine wave which is something like this, which is at the input, so that's what I'm going to see here. So in order to see that, I have to do a different simulation. For that, simulation command should be transient. So this is the transient. Let us try to understand what is this transient, what is this stop time, what is this time to start saving data, maximum step, all those stuff. You can just spend some time here. Assume that I want to see a waveform of 10 kilohertz. How many cycles are there? This is one cycle, this is second cycle. Assume that I want to see 3 cycles. So what is this is with respect to time? The frequency is equal to 10 kilohertz. We know that time is equal to 1 over frequency, which is nothing but 100 microsecond. Meaning for 10 kilohertz, time for one cycle. So from here to here it is 100 micro. From here to here it is another 100 micro. From here to here it is another 100 micro. So if you want to see 3 cycles, how much is the total time that is required? You require 300 microsecond. If the frequency is 10 kilohertz. 10 kilohertz. So in time, in the transient analysis, you should specify stop time depending on how many cycles you want to see. So in this case, assume that if you want to see 3 cycles, you have to give the stop time as 300 microsecond. So this is 300 micro, 300 U. So there is no micro in this. So start time to start saving data. Suppose if you see here, if you want to see the waveform starting from 0th second, so then you say then you say the time to start saving data is 0 itself. So this is 0. And maximum time step, because when you're actually plotting the graph, the simulator will collect the points at each and every small steps. So since you want to have a very smooth waveform, so let us take it for every 1 microsecond the simulation output. So you type it as 1. You keep this value of maximum time step far less than this 300 microseconds. So that's why I just kept it at 1 millisecond. Sorry, 1 microsecond. Now you can see this is dot tran. Suppose if I just take out this, and this is dot tran. You are starting from 0 up to 300 microsecond with an increment of 1 for every 1 microsecond. If I run it now, just a minute, I'll run it now. So what is the waveform that I'm going to see here? Can you see this is a sine wave of 100 millivolt above, and then it is below 0, it is again minus 100 millivolt. If you see here, can you see this is after adding 600 millivolts? So what I'm trying to show you is what is the effect of having the DC source. So this is what I'm seeing. It is 0 to 100 millivolt and it's going up to minus 100 millivolt. That's what is the waveform that is seen here. If I see it here, it is 100 millivolt and minus 100 millivolt plus that 600 millivolt. So it will get shifted here. So that you can see here. I'll come back and I'll try to see the waveform that is there at the gate. Can you see it is shifted above? Can you see this is shifted above? This one is the waveform at gate. So effectively at gate what you have is a waveform something like this. It's centered around 0. It goes up to 700 millivolt and it goes down to 500 millivolt, because it is 600 plus 100, 600 minus 100, which is exactly, you can see. Can you see here? This is exactly, if you want to see that, can you see this is exactly 600 millivolt, and at the maximum you can have 700. Can you see this is 700, 699. Can you see this is 500? Can you see this is 500 millivolt? So whatever you had from 0 to 100 and minus 100 has been shifted to 600 plus or minus 100 millivolts amplitude. So this will certainly guarantee me a current of so and so. So what will be the current if you don't have this sine wave? It will be 400. Okay, let me just come back here and find out. Suppose if of course we are taking Kp is equal to 200 microampere per volt square, and VTO is equal to 0.4, and W by L I just modified it to be 100. So then what is ID in saturation? Then this will be half Kp W by L VGS minus VTO whole square. If you calculate all these things, so substituting Kp as 100 microampere, sorry, this is 200 minus 200 into half, which is 100 micro into 100 into 0. 0.2 whole square, which is equal to, can you see this is 400 microampere, this is 400 microampere. So this will guarantee me a current of 400 microampere. That's what is at this 0.6 I'm getting a current of ID, which is the current due to the DC, as 400 microampere. So now what I'm trying to show you is with this graph, whatever we have, if this is at 0.6 volt, I will get a current of 400 microampere. Over and above this, if I apply some signal, does this current will also increase and decrease? So this current, whatever ID you had, so this ID is due to VGS. Over and above that, this ID, you will have small change. It is due to what? Over and above this 600 millivolt, you are applying plus or minus sine wave. So there is a sine wave which is plus, so this can go up to 100 millivolt maximum and minimum another 100 millivolt. So this can swing from 500 millivolt to 700 millivolt. So that will going to have a change in your ID. So if I just go back and see here, now if I add the current, where is that? Okay, well, I'll just add one more trace. This is my current. See here, current is also changing. Suppose if I put it in different plane, so what I did is let me just delete this pane. So here everything has get mixed up, so you can go here and then add a plot pane. I can add and I can shift the required waveform to this. Can you see now the current is changing? The current is changing here. If you can notice this, okay, there is a from 400 microampere it is going and above and it is coming down. So now we can able to see the change in current also. So now we need to find out what is amplification and all those stuff. So we will just go back to here and then find out what is happening. Can you see this is the circuit what we have? So this is your input signal, input AC signal. This is your transistor. You have shifted it by having some DC voltage. This shifting the waveform from here to here is called as biasing. I think you remember biasing of circuits. So biasing is to make sure that this transistor is on all the time of your waveform, all the time of your waveform. So that's what is biasing stands for. Biasing stands for. So now let us see what happens. So what we actually had was, we actually had a transistor and there was DC voltage and there was a small signal and it was like this and it was this VDD. So which we usually write it as, this was RD. For the circuit analysis we write it as this as VDD and we just write this as MOSFET and this is VGS and this is so and so. You can see this is, let me write it as small v in, this is VGS, this is VGS and this is what? RD, this is VD, this is VN. Now what did we actually had? We had a drain current of 400 microampere for a KP of 200 and WL of 100. Now can you see this AC signal? This AC signal is actually changing around zero, with respect to time. This is your Vin going up to 100 millivolt minus 100 millivolt. Now can you see this is 0.6? That 0.6 is something like this. It is constant, and this 1.8 is also looks like, okay, this is 0.6 and this is 1.8 and this is your sine. So and assume that this is 0. So for this sine wave it will not differentiate this, this and this because all the three are not having any variations, meaning for this AC signal it will not differentiate ground 0.6 and 0.8, meaning when there are DC voltages having a constant amplitude, for this input AC signal everything looks like ground, meaning if you want to write an AC equivalent circuit, you should short this, make this capital VGS 0 and this also 0. So what do you mean by 0? You ground it. So you are grounding this VDD and you are making this 0. I'm shorting it and I'm applying it. This is your RD, and since you are looking at output voltage which is small signal, I will write it as VD. You can see this is capital VD, which was they're at some DC voltage of whatever 0.6 or whatever the voltage, or whatever voltage that depends on this. Now you have a VD, you have a VD here. Now let us try to replace, for analyzing what is the gain of this amplifier, all those things, I should replace this MOSFET by its equivalent model. Now how does this DC voltage was looking like for this? It was looking like a short. So how does this VDD was looking like for this? This was looking like a shorted to ground. So when this and this voltage are treated like ground, then how does this transistor look for this input AC signal? Now when you're applying some DC voltage here, when you're applying some DC voltage, so it was resulting in a current. So when you apply small AC voltage on top of this capital VGS, can you see there is a small change in that current also? That's what we saw here. Can we see there is a change in current also from 400 microampere? Can you see it is going above and below? Now does it mean that this voltage at the input, that is small voltage at the input, which is now, so this is small Vin, does it not become small VGS for this? Small VGS for this. So this small VGS will result in some change in current. It is not capital ID, there is a small ID. So let us try to see this MOSFET, what are the input that this is giving? This is giving small VGS. What are the output you are expecting in terms of, okay, for this change in input voltages, which is over here, this is small VGS. Does this actually result in a change in current, which is ID here? This is ID here, this is around whatever 400 microampere. Will it vary this? Now see, you have a ID which is output, you have a VGS which is a input. How these two are related? These two are related because ID is the output, VGS is the output. So can you see there is a change in your current due to change in VGS? This is given by G. Transconductance of the MOSFET is given by change in ID to change in VGS. Can you see this VGS has changed by plus or minus VG, small VGS? Does this result in a change in ID from capital ID plus or minus small ID? So that's what is this small ID by capital, change in delta, change in ID to change in VGS is nothing but. Now what I can replace this MOSFET as? So this MOSFET, which is gate, drain, source, will look like, can you see this will not take any current, this will not take any current, so this is open circuit. So this is gate, source, this is now open circuit. You will have a voltage VGS between gate and source. Open circuit means there is no current going. Can you see, because of this there is a current that is flowing here between drain to source. I will have a current. This current is of what magnitude? It is GM times, yes, GM times VGS. So this is what? Drain and source. So let me rewrite. For a AC signal, I will just again rewrite the thing. So this is what we had. This was VDD, this was RD, this was capital VD, and you have capital VGS, and you had this as Vin. This was also resulting in some V0. Now how does this look like? That will look like ground. This will be shorted, and you have this. So this is first approximation. This is because now you are not considering any DC parameters, only V0. This is RD. So this was resulting in ID, capital ID and small ID. Since you're not considering capital, so you have only ID here. So this is the current flowing. So how do I now replace this by this? So you retain this V in as it is. This is gate, source, drain. So I'll be replacing this MOSFET, gate, source, drain. Between drain and source I have a current source. I have a current source which is of GM into VGS. So this is between this and this I have a small signal VGS. Now this is gate terminal, this is drain terminal, this is source terminal. So is the source grounded here? Is the V in is between gate and source? Shall I connect it here? Where is drain is connected with the RD and to the ground? Shall I say this is RD and this is my V0? So this blue colored one is the model of MOSFET for an AC signal. So that's why we say this as small signal model of MOSFET. This is AC small signal model is given by this. This is plus minus VGS, gate, source, drain. This current magnitude is GM into VGS. So we will derive the expression for GM will be given by 2 ID Kp into W by L. So drain current, kappa and W by L of the transistor will decide what is GM is. So now since we know what are all these parameters, and of course I can just rewrite this, because can you see this is ground, this is also ground. Shall I replace, shall I just, okay, since these two are same, shall I shift this to down here? I'll simply flip it. So what I'll do is I'll simply connect it here like this. So this I will eliminate. I'll just hold this terminal as it is. I'll put this down here, then this becomes, so is it not V0 now? If I assume a current of I0 flowing this, then what is V0? V0 is equal to I0 into RD. Can you see if this is I0 flowing, can you see it is in the opposite direction of this? So shall I say now I0 is equal to minus GM into VGS, because whatever current that is going in this direction, we are assuming current I0 here, so they are in opposite direction, it is so and so. What is VGS here? Can you see this voltage, is it not same as Vin? I can write VGS as equal to Vin. So then what is V0 is equal to, this I0 is minus GM into VGS is Vin, so this is Vin RD. So now what is V0 by Vin, which is now output voltage by input voltage, which is gain of the amplifier. Since you're measuring the voltage, this is voltage gain. This is voltage gain, which we call it as, which we usually write as AV, is given by minus GM into RD. Minus GM into RD. So AV is given by minus GM RD. So we will go back to this and try to find out what is GM, what is RD, all those stuff. So what we'll do is let us find out what is GM using the equation. So what is GM using the equation? So this was okay 400 micro. So let me just substitute here. It's under root of 2 into 400 exponential minus 6 into, this was 100 into sorry, this is 100, this is 200 micro, 200 exponential minus 6 close. I just edited the same value. You can see it is under root of 2 ID into W bell is 100, and this is kappa. It's actually 4 millisiemens. 4 millisiemens is the value of GM. Now what I'll do, before I just proceed, I'll do dot OP and try to verify how much is the value that I'm getting. So I'll go back here and I'll not do dot tran, I'll do dot OP and try to find out how much is my. Okay, I will run this. Can you see the current is 400 microampere? Go over here and then find out what is GM. Can you see GM is 4 millisiemens? GM is 4 millisiemens. That's what we found okay, using this also. This is 4 millisiemens. So we are trying to just match this GM and that GM. Since RD is equal to how much? 1K, I should get a gain of 1K into 4 milli will be 4 minus 4. Let me just go back here. So what is this GM now? GM is equal to 4. It is minus of 4 milli into 1K. This K and milli will go off. We'll end up with minus 4. So AV is equal to minus 4 is the gain. Okay, we will just verify the gain of the amplifier, whether it is minus 4 or not. We'll just go here and then let me apply a bit small amplitude. I'll show you why it is small required. Okay, this is 10 millivolt. Over and above that 600 millivolt, I'm applying simply 10 millivolt. So if you see the waveform here, now let me do dot tran. This is fine. I'll see 3 cycles. I'm seeing input 3 cycles here. If I see the output here, can you see output is DC shifted and it is having some. Okay, I'll put this here. Let me measure the peak to peak of this. So I know the input peak to peak is from 10 millivolt to minus 10 millivolt. Or is that almost? This is, can you see the peak to peak is almost 20 millivolt? Okay, what I'll do is let me just change this to this here. Okay, peak to peak is, just a minute, I'll move this down here this way so that it is actually 2 minus 1, because you should not be saying that it is minus 20 millivolt. Can you see this is 20 millivolt almost peak to peak at the input. At the output, if you see, the gain is actually minus 4. Minus 4 matlab this should be minus 80 millivolt. I'll just shift it here. Can you see this is almost 80 millivolt? Of course, minus 80. So minus 80 means the gain is minus 4. Why it is minus 4 is, can you see the input is rising here, the output is coming down. It is out of phase. It is out of phase is the representation of this negative sign. Negative sign. The magnitude ratio is, this is 80 millivolt peak to peak. This is 20 millivolt. So how much is 80 by 20? So I can find out what is the gain as, because I had, okay, let me just go back and put it here. This is how I had the input. So this was my input, which is varying from, it's around 0, it was going up to 10 milli, and this was going up to minus 10 milli. The output is centered around 1.4 volt and it is going like this, and it is going like this. If you see the peak to peak of this I'll say it as V0 peak to peak. Let me take only the magnitude. This is V in peak to peak. So how do we define AV? The gain in terms of magnitude is V0 peak to peak by V in peak to peak. V in peak to peak. So when I say peak to peak, it is this peak to peak and this peak to peak. This peak to peak we found out it as 80 millivolt, and this is 20 millivolt. This will go, and you can see this will also go. This will become 4. So magnitude of the amplification is 4. How do you get that minus 4 is, this minus 4 can be written as 4 at an angle 180 degree or plus or minus 180 degree. So what is this plus or minus 180 degrees? Because when if you want to represent negative, so it is the magnitude is 4, the phase If the input is increasing, output is reducing means, so it has got a phase shift of 180 degree. So that phase shift of 180 degree, you can write it as 4 at an angle 180 degree, which is nothing but minus 4. Minus 4. So that's what you're seeing here. See here, this is my input voltage around 0 going up to 10 millivolt minus 10 volt. This is centered around 1.4 volt and it is going below 40 millivolt. There it is above 40 millivolt around 1.4. So peak to peak is 80 millivolt. Here peak to peak is 20 millivolt. So the gain of the amplifier is minus 4. Why that minus sign? It is because of this phase shift. This is input is going like this, output is going in the opposite direction. If the output was also going in the same direction, then there was no phase shift. Then this would have been only plus 4. But since your equation says that you should get minus 4, you are getting exactly minus 4. Thank you so much.